kind introduction. Okay, thank you. Today, I'd like to talk about optical cantilever by combining optical lever method and sampling Moiré method and on-chip pattern laser. In recent years, optical lever-based force and displacement sensors have been widely used in various fields. The application includes biological measurements such as cell mass detection and insect vibration analysis, as well as surface properties of materials. These optical lever-based sensors can detect tiny forces and displacement in the nano to micro range. So high resolution is required for such measurements. Main reason these sensors can measure with high resolution is the principle of the optical lever method. The principle is simple. It uses a laser, a cantilever, and a photodiode. Light from the laser reflects on the cantilever and goes to the photodiode. Small l indicates the cantilever length, and capital L indicates the distance between the cantilever and photodiode. When the cantilever bends, the reflected light shifts twice the cantilever bending angle. Also, the displacement on the camera, xp, and the cantilever displacement, xi, are related by the ratio of capital L to small l. So photodiodes can detect the cantilever displacement with amplification. However, we must align the reflected light to the center of the photodiode at the start of the measurement. To solve this problem, our research group have proposed this sensor system. It consists of a cantilever with a diffraction grating, a monochromatic laser, and a lensless camera. When light reflects from the cantilever, a diffraction pattern appears on the camera plane. By using sampling Moiré method to analyze this pattern, we can calculate the cantilever displacement. The sampling Moiré method will be explained later. In this method, optical alignment is easy because the multiple diffraction patterns were used for measurement analysis. In addition, it employs the sampling Moiré method. High resolution displacement measurement can be achieved. However, it requires additional fabrication to form multiple slits on the cantilever. On the other hand, recently, on-chip pattern lasers based on semiconductor lasers have attracted attention. They can project many kinds of patterns directly without using other optical elements by designing the laser structure. The laser is compact with a micrometer scale emitter and offers high mode stability as well as high directional beam control. As an application of this laser, it has been used for flow velocity measurement in microchannels. The laser is designed to project a stripe pattern and function as a Doppler flow meter. Because the laser is compact and can project stripe pattern directly, it enables easy optical alignment even in small measurement areas. In this study, we propose a new cantilever sensor system that combines this previously proposed method with an on-chip pattern laser. It consists of a cantilever, a lensless camera, and an on-chip pattern laser. This laser projects a stripe pattern, and the pattern is analyzed by using sampling Moiré method and calculate the cantilever displacement. This method has two advantages. First, it can capture a stripe pattern without any optical elements. Second, it doesn't need a diffraction grating, so the fabrication process of the cantilever becomes easier. Therefore, our proposed method simplifies the conventional optical lever method while maintaining high resolution. Here is the principle of the sampling Moiré method. Sampling Moiré method is one of the image analysis methods and treats shift in a stripe pattern as a phase shift of a periodic waveform. It is possible to measure displacement with a resolution much higher than the pixel resolution of the camera. Although I skipped the detailed math here, this method can detect the pattern movement as small as 1/1000th of the pattern pitch. In this study, we combine these technologies with the optical level method. We analyze the shift of the laser pattern by using sampling model method and calculate the cantilever displacement. Here is the cantilever design. It is made of 75 micrometers glass, and it has a 5 millimeters square plate and zigzag feed. After the design, we simulated the spring constant of the design cantilever by FEM simulation. This figure shows a displacement when a 1 millinewton force is applied. The spring constant was calculated with 2.3 Newton per meter. Here is the fabrication process of the cantilever. Fabrication process is very simple with only 2 steps. First, we cut glass into the cantilever shape but with a UV laser. This video shows laser processing at 5 times speed. It takes about 5 minutes for one cantilever. Next, we clean the cantilever by ultrasonic cleaning and deposited chromium and aluminum. Deposition takes about 20 minutes, and after that we fix it on a 3D printed jig and measure its spring constant. The spring constant was 2.0 Newton per meter, which was close to the simulation value. Okay, next we built the measurement system and evaluated the sensor response. Here is the experimental setup. It included a lensless camera, on-chip pattern laser, and fabricated cantilever. A metal jig was attached to a piezo stage was used to push the cantilever. When the cantilever is placed, the reflected light also shifts. Here is the on-chip pattern laser used in the experiment. The pitch of the stripe pattern was defined by the split angle of the pattern laser. The split angle was designed to be 0.414 degrees, and pitch of the stripe pattern changes with distance from the on-chip pattern laser. The wavelength was 940 nanometers, and we applied 15 voltages DC to the laser. Here are the dimensions of the setup. The laser angle was 45 degrees, and both the laser and the camera are 30 millimeters from the cantilever. From the split angle of the pattern laser, the stripe pitch was calculated to be 0.43 millimeters. We recorded the pattern shift for 8 seconds at 60 fps. Here is the recorded pattern shift. When the cantilever is placed, the reflected pattern can be observed to shift like this. And we analyzed 6 stripes near the center of the pattern. The analyzed area shown by the red flame consisted of 1 by 800 pixels. The pitch was 0.47 millimeters, and we then analyzed this movie by using sampling model method. Here are the results. The blue line shows the piezo stage displacement, and the orange line shows the pattern shift analyzed by the sampling model method. The pattern shifts as the piezo stage is displaced, and the movie was able to be analyzed by using the sampling model method. Also, this is based on the optical level method. The cantilever displacement was amplified on the camera plane. In this experiment, the displacement was amplified 11.7 times. Next is the noise level. We recorded the pattern while keeping the cantilever still and analyzed it in the same way. The noise level was 808 nanometers. This is one of 500 of the pattern pitch, matching the principle of the sampling model method. Dividing this by the amplification factor 11.7 gives the displacement and force resolution of the cantilever. They are 69 nanometers and 138 nanonewtons. This shows our proposed method can measure this for displacement and force with high resolution. This is the conclusion. We propose optical cantilever using on-chip pattern lasers and sampling model method. The captured pattern shift was analyzed by using the sampling model method and measured with high resolution. Thank you for attention.